Cache memory, L1, L2, L3. Here is your same structured beginner-friendly content for cache memory, L1, L2, L3, intermediate level introduction. As CPUs became faster, a major problem appeared. Memory was too slow compared to the CPU. To solve this, computers introduced cache memory, a small but extremely fast type of memory located close to or inside the CPU. Cache helps reduce delays by storing frequently used data and instructions, allowing the CPU to access them quickly. At this level, you will learn what cache memory is, why it is important, types of cache, L1, L2, L3, how cache improves performance, how cache interacts with RAM. Understanding cache memory is critical for learning CPU performance optimization and system efficiency. What is cache memory? Cache memory is a small, high-speed memory that stores frequently used data so the CPU can access it quickly. In simple terms, cache equals fast temporary memory for frequently used data. Example concept. CPU means checks cache, means if data found, means fast access. Why cache memory is needed? The CPU is extremely fast, but RAM is slower. Example concept. Fast CPU plus slower RAM means delay. Without cache, CPU would constantly wait for RAM. Performance would drop significantly. Cache solves this by acting as a bridge between CPU and RAM. Memory hierarchy. Context. Cache is part of a layered memory system. Registers means L1 cache, means L2 cache, means L3 cache, means RAM. Registers means L1 cache, means L2 cache, means L3 cache, means RAM. From fastest to slowest. Registers, L1 cache, L2 cache, L3 cache, RAM. Types of cache memory. Cache is divided into three main levels. L1 cache, L2 cache, L3 cache. Each level balances speed versus size. L1 cache. Level 1 cache. What is L1 cache? L1 is the fastest and smallest cache, located directly inside the CPU core. Key features: extremely fast, very small, typically KBs, dedicated per core function. Stores the most frequently used instructions and data. Example concept. CPU means L1 cache, means immediate data access. L2 cache, level 2 cache. What is L2 cache? L2 cache is larger than L1, but slightly slower. Key features: larger than L1, slower than L1, maybe per core or shared function. Stores data that is not in L1, but still frequently used. Example concept. L1 miss means check L2 cache. L3 cache, level 3 cache. What is L3 cache? L3 cache is larger but slower than L2. It is usually shared among all CPU cores. Key features: largest cache level slower than L1 and L2, shared across cores. Acts as a backup cache before accessing RAM. Example concept. L2 miss means check L3, means then RAM cache access flow. When the CPU needs data, it checks memory in this order. CPU means L1 means L2 means L3 means RAM. CPU means L1 means L2 means L3 means RAM. Step by step. CPU checks L1 cache. If not found, means checks L2. If not found, means checks L3. If not found, means fetches from RAM. Cache hit versus cache miss. Cache hit. Data found in cache means very fast. Cache miss. Data not found means fetched from RAM means slower. Example concept. Cache hit means fast. Cache miss means delay. Why cache improves performance. Cache reduces the time needed to access frequently used data. Example concept. Frequent data means stored in cache, means faster execution. Benefits. Reduces CPU waiting time, improves instruction execution speed, increases overall system performance. Cache size versus speed trade-off. Cache design balances. Speed, size. Example concept. Small cache means very fast. Large cache means slower but more storage. Summary: L1 means fastest, smallest. L2 means medium speed and size. L3 means largest, slower. Real-world example. Opening a frequently used app. First run means data from RAM. Next runs means data stored in cache means faster loading. Cache and multi-core CPUs. In multi-core CPUs, L1 and L2 are usually per core. L3 is shared among cores. Example concept. Core 1 plus Core 2 means shared L3 cache. This allows cores to share data efficiently. Cache coherence. Advanced idea. When multiple cores use cache, they must stay synchronized. Example concept. Core 1 updates data means Core 2 must see updated value. This is managed by cache coherence protocols. Common performance factors. Cache performance depends on cache size, cache latency, cache levels, CPU architecture. Example concept. Better cache means better CPU performance. Advantages of cache memory. Advantages include faster data access, reduced memory latency, improved CPU efficiency, better multitasking performance. Example concept. Cache means faster system response. Limitations of cache memory. Challenges include limited size, expensive to manufacture, complexity in multi-core systems. Example concept. Small size means cannot store all data concepts learned. What cache memory is. Difference between L1, L2, L3. Cache hit versus miss. How cache improves performance. How CPU accesses memory. Simple definition. Cache memory. L1, L2, L3. A small, fast memory system that stores frequently used data to speed up CPU operations. Final summary. Cache memory is a critical component that bridges the speed gap between the CPU and RAM. It is organized into multiple levels, L1, L2, L3, each balancing speed and size. By storing frequently used data closer to the CPU, cache reduces delays and significantly improves performance. Understanding cache memory helps explain why some CPUs perform better than others and how modern systems achieve high efficiency.